Hello again, class. We are going to continue with Chapter 2, Section 3 on continuity. We are not going to do the whole section, probably about half or 2/3 of the slides. In this chapter, this section, we'll be talking about continuity. What is continuity? The definition of continuity, the properties of continuity, and then being able to solve some inequalities, those continuity properties. As you have seen in some of our previous graphs, there have been, you don't see it in this one, but there are holes. There are holes in a graph. There are vertical asymptotes like this one, and then again, they're not in this graph, but horizontal asymptotes. But either way, they're irregularities and they are breaks in the graph. So, what is the definition of continuity? This is important. This is part of your lesson for the week. A function is continuous at a point x equals c if the limit of f of x exists as x approaches c, number 1 here, as x approaches c. The function is continuous if the function exists when you plug in your value for c. And then the function is continuous if the limit at f of x as x approaches c is equal to f of c. So basically number 1 is equal to number 2. And all 3 of these things need to happen for the function to be continuous at point x equals c. So let's take a look at this example. If you remember from section 2.1 and I believe even 2.2, we have used linear equations to give you a real base idea of what these concepts like continuous and infinity are, because they're the easiest to understand. And so let's take a look at what's happening here at f of x equals x minus 1. We're looking at the point x equals 2. So in this case, c is equal to 2 based on our previous definition. So you can see here, we're going to go through all 3 properties of a continuous function. And so we find the limit of x minus 1 as x approaches 2. And so all they did is they plugged the 2 in right here for x. So 2 minus 1 is equal to 1. And so the limit exists. Good. Check mark. Now we plug in our value for x equals 2 into our original function. And so here they're saying 2 minus 1 is equal to 1. So a value exists at x equals 2. Check. Now the last part of this test to determine if a function is continuous is number 1 equal to number 2? And it is. The limit at x of x minus 1 as x approaches 2 is 1, and f of 2 is also 1. So this checks out, and the function is continuous at x equals 2. Let's take a look at another example. This is a rational function. So the first function was linear. This is a rational function. So let's do all of the properties now of this rational function using the properties of a continuous function. Now you can see here at number 1, they come up with this value minus 6. And so if you can remember for limits that maybe do not exist, because if you were to plug in x equals minus 3 into this function, that limit would not exist. So how did they come up with negative 6? Well, if you can remember, you can factor out this difference of squares right here, and this factors into x plus 3 over x minus 3, because it is a difference of squares, all over x plus 3. So this is just a little trick that you can use, and you can see that x plus 3 and x plus 3 cancel, and you can only do this because they're multiplying across. If this was x plus 3 parentheses and there's a plus sign in the middle, you wouldn't be able to cross it out, but everything is multiplied across. And so now you're left with x minus 3, and so all you have to do is you plug in this minus 3 in here, and that gives us minus 3 minus 3, which is negative 6, which is how they got this answer here. So the limit exists if we reduce the fraction. That is key here. However, if you plug in this x equals negative 3 into your original function, this is the original function here, x squared minus 9 over x plus 3. The function is undefined. You will not, it's 0 over 0. The numerator is 0, the denominator is 0, and anything divided by 0 is undefined. So this does not check out. 1 checks out, number 2 does not check out, and because number 2 does not check out, number 3 does not check out, and this is a not equal sign. The limit at x squared minus 9 over x plus 3 is not equal to the function when we plug in minus 3. Because all three things do not happen, the function is not continuous at x equals negative 3. And so you can look at this graph here. It's not complete. They zoned in. So you can see that it has a hole here at x equals 3. All right, so let's take a look at this absolute value function. This absolute value function is x, the absolute value is around the numerator, and then over x. But we're going to look at it when x equals 0 and when x equals 1. Take a look at x equals 0. Well, you can look at the graph and you can see that number 1, there's holes, and there is this break here. So the function as the limit of absolute value of x over x as x approaches 0 does not exist here. It does not exist, so it does not check out. Does not check out. Again, if we plug in this 0 here to the original function, we have another 0 over 0, and anything divided by 0 is undefined. So that number 2 does not check out. And because number 2 does not check out, we have this do not equals sign, because number 1 is not equal to number 2. Okay, so the function is not continuous at x equals 0. However, let's do everything again for x equals 1 right here. So we have the limit as x approaches 1, the absolute value of x over x, and that is equal to 1. The function f of 1 is also equal to 1. And so therefore, this is 1, this is 2, and this is 3. The limit as x approaches 1 of the absolute value of x over x is equal to f of 1. And so you can see that it is continuous as x approaches 1, and this is 1 right here. and that's this little spot. So you can see it's continuous, but it's definitely not continuous at 0. All right, so let's talk about continuity properties. If two functions are continuous on the same interval, then their sum, their difference, their product, and their quotient are continuous on the same interval. That's key here. Except for the values of x that make the denominator 0, because anything divided by 0 is undefined. Okay, so here are some examples of continuous functions. A constant function is continuous for all values of x. So this is x equals 3, okay? Or y equals 3, okay? Constant. For integers where n is greater than 0, basically here your exponent is not negative. It is continuous for all functions. Okay, a polynomial is continuous for all functions. Polynomials are, right, x squared, x cubed, right? And then, ax squared plus bx plus c, things of those natures. A rational function, which was like that x squared, like the second example, x squared minus 9 over x plus 3. It is continuous for all values of x except, there is an except here, the values that make the denominator 0. So just like in example 2, x equals -3 made the denominator 0, and so is continuous except for that particular value of x. Odd positive roots. So this is a cubed root, the 5th root, 7th root, etc. is continuous as long as f of x is continuous. So if there is a point where f of x is not continuous, this root is also not continuous. For positive integers, root, so this is the square root, right? Square root to the 4th root, etc. Okay, is continuous where it is not, f of x is not negative, right? You cannot take a negative. All right, so we are done here. We're not going to discuss sign charts, and you will now move on to section 2.4.